Page 1 of practice exam 3 leads off with a ranking question. Rank the following compounds in order of their acidity. So 1 being the lowest pKa or the most acidic. All right, so you want to evaluate this based on the most acidic hydrogens. All right, so here we have alpha hydrogens. These are alpha to 2 carbonyls, so the conjugate base will be stabilized via 2 resonances. Okay, that's the same as this molecule over here. All right, compared with the alpha hydrogens on this carbon, which are equivalent to the other 3 alpha hydrogens. All right, and the conjugate base there will only be stabilized by the 1 carbonyl, all right, as well as these 2 on the cyclic amide. All right, so the 2 end molecules, again, have 2 resonance forms that will stabilize the conjugate base. The 2 middle ones will only have 1 resonance form that stabilizes the conjugate base. All right, so the one with more resonance, more stable in terms of conjugate base, which means that the protons are more acidic. All right, so the question is, which is more acidic, a diketone, so a 1,3-diketone, or a beta-keto ketone, versus a beta-keto ester? Okay, now remember that the ester has a lone pair on the oxygen that can donate into the carbonyl carbon, which makes it less partially positively charged, all right? Which means that it's going to stabilize the conjugate base less, okay? And so the diketo ester is going to be less acidic than the diketone, all right? So our diketone is our most acidic, and the beta-keto ester will be our next acidic. Okay, and likewise with our ester, we have a cyclic amide here. Okay, this lone pair can donate into the carbonyl, again making it less positive, which means that it will stabilize the conjugate base anion less, which makes the proton on this molecule less acidic. All right, so it will be the least acidic compared to the diketone. Okay, well really, it's not a diketone, even there's 2 ketones on the molecule, but each conjugate base will only be stabilized by a single ketone. All right, the next question is quite difficult. I wanted to make this challenging for the practice exam. So this is a question of aromaticity. All right, so these 5-membered rings that have the diene species on them, okay, this is called pyrrole. All right, so we've got a lone pair on each one of these nitrogens. Okay, and again, remember, electrophilicity has to do with how much partial positive character a carbonyl has. All right, in order for something to have less partial positive character or be less electronegative, electrons have to be donated into the carbonyl from a heteroatom. Okay, what's tricky about this question is, so we can draw the simple, donation of electrons into this carbonyl here, and we can draw it twice for these amines. Okay, the trick here is that these lone pairs will not donate into the carbonyl, and why? It's because they are contributing to the resonance, the aromaticity of the 5-membered ring. Okay, so they will not donate into the carbonyl carbon. And so all that these nitrogens will do is they will actually activate electrophilicity via induction, right? It's a polar covalent bond. Nitrogen's pulling on those electrons, so it has the inductive activation of the carbonyl without the resonance donation due to aromaticity. All right, so that makes this molecule our most electrophilic. This would be our next electrophilic. Okay, and then for these non-aromatic nitrogens, okay, the more donation you get into the carbonyl, the less electrophilic it is. All right, so this molecule is going to be our least, the one on the left is going to be our least electrophilic because it has 2 nitrogens donating in electrons into that carbonyl carbon, making it less positive. All right, and the rightmost molecule does that just once. Alrighty. All right, the last question on the first page. Rank the following compounds by the basicity of their most basic nitrogen. All right, the first molecule, there's no lone pair on this nitrogen. This lone pair is tied up in aromaticity. So this is essentially going to be completely non-basic. All right, so that's going to be our least basic. All right, here we have, this is an sp2 hybridized nitrogen. Why? Because this lone pair is tied up in resonance with the aromatic ring. Here we have a nitrogen that is also sp2 hybridized because it's tied up in resonance. However, this is going to push electrons down to this nitrogen. So this nitrogen will have a partial positive charge in resonance. This nitrogen will have a partial negative charge. Okay, here we have another sp2 nitrogen that's going to have some partial positive character. And here we have an sp2 lone pair on nitrogen that's never going to have a direct negative charge, okay? But because this lone pair is donating into the ring, this ring is going to be more electron rich, which will help with the basicity of the sp2 nitrogen, okay? So, since this nitrogen is partially positively charged, okay, that's not going to be very basic, all right? This third molecule has a delta minus on a nitrogen, so this is going to be our most basic nitrogen. We have that delta minus. All right, this will be our number 2 basic. This will be our number 3. All right, because again, this sp2 hybridized nitrogen, or the lone pair that's sitting in that sp2 orbital, has no partial positive charge, and so it's going to be the most basic nitrogen on that molecule.